Welcome everyone to this edition of our weekly seminar or lecture series on evidence, models, and explanations in science. And we have with us today Professor Prasanta Bandyopadhyay, who I'm sure many of you know. Prasanta has been a major supporter and participant of our organization here of PhilSci India, and really been a huge encouragement to the discipline of philosophy of science in India, besides being an accomplished philosopher of science in his own right, who works largely on the philosophy of statistics. And today we're going to hear from him about climate modeling. And so I'll hand it over to Prasanta for the talk. Yeah, go ahead, Prasanta.
Thank you, Tarun. I'm very pleased and honored to receive that invitation to speak before the distinguished Indian philosopher of science. I'm thankful to Tarun, Dawn, Joby, Philos, Shinod, and lots of other people who are working behind the scene to make it a success. And so I am going to talk about a paper, but before I say, after such a glorious introduction, if you see any errors on my slides and kinds of thing, and if I fail to answer any question, these are all will be fall on Dawn, because Dawn is supposed to look at it very carefully. So the blame will go to Dawn. So without much ado, let's start with that. So this is a paper co-authored by 5 people apart from me. Our student Kevin Beiser, who was a student at MSU and also studied at NYU. Priyantha Vijaya Antung, University of UME, and internationally famous climate scientist Steve Running from University of Montana. And our stat colleague, Stacy Hancock from Mathematical Statistics Department. So, in school, we read all the 4 Vedas, and now we have got a new Veda on causal inference. So sometimes it's good to fall back on the testimony. So I'm starting with a quote from Judea Pearl. It is again fictitious, and fictitious examples like Einstein's thought experiments always provide a good way to probe the limits of our understanding. I usually pay a great deal of attention to what philosophers have to say about slippery concepts such as causation, induction, and the logic of scientific inference. Philosophers have the advantage of standing apart from the hurly-burly of scientific debate and the practical realities of dealing with data, unquote. And I'll come back to that later on in the talk. So you can expect these are the 4 things I'm going to talk about in my paper. First, I'll talk about the debate between those who question about the climate model ensemble prediction and those, the group we belong, where we are trying to defend the climate model ensemble prediction. But one thing we need to make it clear, those who are questioning the assumption of climate ensemble model prediction, they are not climate deniers at all. So you just want to make sure about that. So in that line, those who are questioning or contesting the model assumptions and the reliability of the ensemble prediction, the kind of reasoning they fall back is the Bayesian reasoning, because Bayesian reasoning is taken to be the a received view in philosophy of science. So by using Bayesian reasoning, what these skeptics about the climate ensemble model prediction are arguing that that there are issues if you use Bayesian reasoning in a correct way, we won't see any increased confidence in climate model ensemble prediction. So what we are going to do is that first we are trying to make their arguments much more stronger than they took them to be. So by making a distinction between model dependence and correlation. And their claim is that because model inside the ensemble models are dependent, so therefore they cannot provide they cannot provide robust prediction. So the last part of the paper is the longest part, where we are providing a Bayesian defense of confidence in ensemble prediction and showing why there is a way we can argue that we can have an increased confidence in climate model prediction. So here's the debate. So as it is being clear that increasingly climate scientists rely on ensemble model prediction to forecast and test some predictive hypothesis, let's call it H. So in London School of Economics, there are philosophers and recently statisticians also joined the group, where they are saying that if the model is actually nonlinear, then minor imperfections could generate misleading predictions, and therefore we cannot rely on the prediction. So because the probabilistic prediction or forecast are not that reliable, so they fail to provide a guide about public policy. So Wendy Parker, she's a philosopher of science, argues that we should increase confidence in robust model prediction in predictive hypothesis H if the Bayesian theory approves it. And again, Bayesian theory is taken to be the received view of philosophy of science. Parker continues and argues that actually in climate ensemble prediction, what we see that given the data, probability of data given the predictive hypothesis H is not appreciably higher than probability of data given the negation of that predictive hypothesis H. She, along with a very well-known climate scientist, Knutti, argue that models are often mistakenly taken to be independent sources of information, quote, when biases in their performance have been found to be correlated. So, debate continued. So consequently, they contain that if the model ensembles, that means models, small models inside the ensemble, are dependent and correlated, they are shared information and many lines of code, then they fail to provide the independence or the strong support for the predictive hypothesis. So the dependency, one thing we need to get clear about is the dependency or the independency of model in climate's ensemble seems to be very important right now in climate science literature, not just in philosophy of science. So here, just to make sure what we are arguing, what is our thesis? So first, we are going to argue that to strengthen the argument provided by or offered by Knutti and Parker, we are going to make a distinction between dependence and correlations among models. So to make a different distinction between probabilistic dependence and the correlations of models. Then using statistical notion of dependence of model, and which is taken to be an open question in climate science, we show that we can have an increased confidence in the predictive hypothesis. Then we further demonstrate that actually we can have an increased confidence in H, the predictive hypothesis, irrespective of the fact whether models are dependent or independent, provided we satisfy a formal condition. Okay, so this is our three theses. So now let's launch into Parker's argument against Bayesian confidence. So, so here is Parker's pessimism about climate models contribution. What climate model ensemble model prediction cannot do. So what she does in her philosophy of science paper,
Prasanta, can you define Bayesian confidence?
By Bayesian confidence, Mark, let me finish the talk. So by Bayesian confidence, I mean is that we have, but yes, we have a prior and we have likelihoods and we have priors over the likelihoods, and you get the credible interval if we, of course, we do the main thing, averaging over the models. But the problem is that, not problem, actually the advantage is that the Parker is actually taking H to be simple statistical hypothesis, so we don't need to have the prior over the likelihoods. So the straightforward, straightforward averaging, whether we don't need any prior for any models, probability of model under the hypothesis. May I go ahead, Mark?
So yeah, sorry, go ahead, please go ahead, Prasanta.
So when climate models, ensemble multiple computer simulated models agree on some predictive hypothesis H, some robust prediction that most of the models inside the ensemble model say that H is true, then she asked the question, what is the epistemic significance of this agreement? And then she posits three potential answers to this question. The first one is that agreed on predictive hypothesis H is very likely to be true. Significantly increased confidence in H is warranted. And third, security of a claim to have confidence for H is enhanced. But what she did, she rejects all of them and concluding that actually it has a very little or no epistemic significance. So here is a statement of Parker's pessimism about climate models contribution. Three premises, one conclusion. And so maybe I should be a little more careful. So here Parker reconstruct the Bayesian approach that might seem to contribute to the increased confidence in ensemble model prediction. So she has three premises and conclusion, and she is going to challenge some of the premise to argue that the whole argument is deductively valid but not sound. So here are the three premises with a conclusion. D warrants significantly increase, the data warrants significantly increased confidence in the predictive hypothesis H if probability of data given the hypothesis is substantially higher than the probability of data given the negation of the hypothesis. So basically what is the first premise of her argument or the Bayesian approach is the probability, if the probability of data given H is substantially much higher than the probability of data given the negation of the hypothesis, then data should provide warrant for increased confidence in the predictive hypothesis. Now, the premise two is actually the robust model prediction. All of the models or most of the models inside the ensemble indicate the predictive hypothesis is true. And the third one is the observed agreement among models is substantially more probable if H is true than if H is false. So, that is the probability of data given the predictive hypothesis is substantially higher than the probability of data given the negation of the hypothesis. So therefore, from the three premises, conclusion follows that data warrant significantly increased confidence in H. She argues that the third premise actually fails in this case and undermining the Bayesian argument and showing why the Bayesian argument for increased confidence is actually unsound. So her defense of premise one, and premise one is that if data given the predictive hypothesis is substantially higher than the probability of data given the negation of the predictive hypothesis, then the H will be confirmed. She takes it to be part and parcel of the Bayesian framework. That is, data warrant increased confidence in a hypothesis if and only if data given the hypothesis are significantly more probable than the data given the negation of the hypothesis. And the second premise, as I told you, that data, that means all or most of the model inside the ensemble model prediction indicate that predictive hypothesis is true. Now, just we have a small point here, which it's not going to affect the talk at all, or Parker's argument. So that her argument that that what she takes the part and parcel of Bayesian framework. That means data given the hypothesis, if data given the hypothesis is greater than probability of D given not H, then probability of H given D is higher than the probability of H. That holds only when H and not H are mutually exclusive and jointly exhaustive. And that one could have a case if this assumption is not followed, then we can have a case where you have a very strong confirmation, but we have, we have probability of data given H is actually less than probability of data given the negation. For the rest of the talk, we go with her assumption H and not H are mutually exclusive and jointly exhaustive. So what is her reason? What is her rationale for why she thinks that premise 3 is questionable. She has at least 3 reasons. Her first reason is that models being actually nonlinear are susceptible to initial conditions, and that lead to the models being unreliable in terms of the prediction. Second reason is that that the model make use of past data, and simply those past data do not work in case of climate science predicting about the future climate change. And one example, not from her paper, but other places, is that Arctic region, which had a lot of ice sheet, but now depletion of ice is occurring. So past data cannot be a predictor of the future data. And a third reason is that any model contains lots of idealization. And those idealization are most of the time do not work, and especially in terms of, with regard to the ensemble model prediction. And also tuning of model is one of the things to fit the observation. That means we fit a current model to the past data, but that tuning doesn't sometimes, many of the times do not work with respect to future data. So these considerations, among others, lead Wendy Parker to challenge that the inference from the probability of data, given the predictive hypothesis, is not substantially higher than probability of D given not H. So if probability of D given H, yes, so her point is that because of the reason, we cannot conclude that probability of data given the predictive hypothesis is substantially higher than probability of data given the negation of hypothesis in climate ensemble model prediction. So section 3, model dependence correlation distinguish. So Knutti, as I mentioned, a very well-known climate scientist, says that in his 2019 paper that model dependence is an open question in climate science. And he offers the reason why it is such an important issue. In climate model simulations, actually, they are not necessarily independent. Since model building, scientists share software code, concepts, subjective knowledge, and additionally, there is the legacy code, the code that has been passed down from one generation of simulation to next. Simply put, as Knutti and his co-authors write, unquote, biases of individual models are correlated, unquote. So referring to the, the CPI-P3, the couple model intercomparison project, they conclude that, quote, sophisticated statistical methods also suggest that the equivalent number of independent models, it's much smaller than the total number of models. So there are very few independent models inside that ensemble model we are talking about. Now, Wendy Parker joins Knutti in this argument, and she writes that the sources of the models are not independent, as codes, algorithms used by different, different models are correlated. As a result, their predictions are biased. It would seem that for Parker, Knutti, and Knutti's co-authors, being dependent and being correlated are virtually interchangeable. That is, if two events or models are correlated, then they must be probabilistically dependent and convergent. But sometimes philosopher science make a criticism about analytic epistemologists or analytic philosopher that we make too much minor, small distinction without much significance. But maybe it is not like that. We just want to strengthen their argument. So here is the case. We are going to show that there's a difference between the notion of model being dependent and model being correlation. So when X and Y are correlated, of course, X and Y are probabilistically dependent. But when X and Y are probabilistically dependent, they may or may not have a non-zero correlation. This is because correlation actually measures the linear relationship. And so here is an example, the one, so we probably say Y equal to X squared. And X has a uniform distribution over the interval plus minus 1 to 1. The two variables are exactly probabilistically dependent, but they have a zero correlation. So we need to make a distinction that actually they are talking about model dependence. They are not talking about model correlation. And that's why they're, it's important to make a distinction. Now, again, one might think why we are digressing, why we're not focusing on the whole thing, because this is a small distinction. It is not. There's a long history in statistics and also in philosophy that people making the confusion between dependence, probabilistic dependence, and correlation. So here is a long history actually dating back to Carl Pearson. Lehman, it's a quote Lehman has, and Deborah Mayo quoted it. So, so it has been noted that Carl Pearson himself made the mistake, quoted in Mayo, quote, Neyman found Pearson himself surprisingly ignorant of modern mathematics. The fact that Pearson did not understand this difference between independence and lack of correlation led to a misunderstanding that nearly terminated Neyman's stay in London, England, actually. So it's not something that happened 100 years ago. Philosophers and statisticians are absolutely clear about the distinction. So here is we have two very well-known now young philosophers. They're probabilist Alan Hayek and Chris Hitchcock. They repeat this oversight when they write, if probability of A and probability of B is not equal to probability of A multiplied by probability of B, then A and B are probabilistically dependent or correlated. So this is from their book, handbook, Philosophy of Probability and Philosophy. So these quotes are illustrative of the fact there's a long history of conflicting correlations and dependence of events, even among very famous eminent scholars. So we are just strengthening that argument, focusing our argument where we need to look at carefully. So obviously, we are not claiming that Knutti and Parker, they do not know the difference. So we agree with them that the ensemble models are dependent for the consideration, exactly the consideration they have offered along with the climate scientists. So, but in the next section, we are going to argue, even though models are dependent, we can still have a, models are dependent in the probabilistic sense, we can still have an increased confidence in ensemble model prediction, predictive hypothesis H. So that is the last section, it's the long section, Bayesian defense of an increased confidence interval. Increased confidence. So, so although climate models are not totally independent, they are not clones of each other. These models are so huge that there are many places in the development and execution where climate models differ enough that they provide a different look at the same hypothesis. As a result, when they agree on a certain hypothesis, our confidence in the result should be higher. But it is true the confidence cannot be reached 100%. And more the models that still support the hypothesis, the stronger the conclusion will be. So now we are going back to a quote we started with, it's by Pearl. So it is again fictitious, but fictitious example like Einstein's thought experiment always provide a good way to probe the limits of understanding. I usually pay a great deal of attention to what philosophers have to say about slippery concepts such as causation, induction, and the logic of scientific inference. Philosophers have the advantage of standing apart from the hurly-burly of scientific debate and the practical realities of dealing with data. So we take this epigraph from Pearl to heart about how fictitious example is actually illuminated the complex labyrinth of scientific inference. And we hope that if executed properly, our example should provide the epistemological underpinning of ensemble model prediction. Now, this is not a place of a full-length discussion of a defense and rebuttal for the use of thought experiment. And here are a book 20 years ago written by Sorensen, which is a good book, and a recent collections of articles by Stewart. One can look at it for a full-length discussion. So what happens? So different organization in CPI P6 take 10 or more ensemble members to reduce noises and biases. So we therefore take 10 models for our example. So again, for Bayesians, our Bible is Bayes' theorem, and the Bayes' theorem is that probability of the posterior probability of H is equal to the prior multiplied by the likelihood, how likely is the data, divided by the marginal probability of data, where marginal probability is of course greater than 0. So our counter confirmation, which is nothing new, states that data confirms H if and only the posterior probability is higher than the prior. And again, to know the posterior probability of H, we need to know the prior of H and not H. Remember, we are going with Parker's assumption that H and not H are mutually exclusive and jointly exhaustive. And we need to know whether the H is confirmed, that means the posterior probability higher than prior. We need to know the likelihood probability of data given the predictive hypothesis, and the probability of data given the denial of the predictive hypothesis. But what happens is that probability of D given H is not known. It needs to be estimated by using other conditional probabilities. So consider D1, D2, capital D1, capital D2, capital D3 to D10 to be prediction data under each model, M1, M2, M3, M10 that confirm H. So let me make it clear. So we have a big ensemble model, and inside that model, we have small 10 models, small M1, small M2, small M3, small M5, ... small M10. So probability of small d1 given M1 is equal to capital D1. That's we call prediction data. Probability of small d2 given small m2 is equal to capital D2. So this is how we are taking D1, capital D2, D3 to be the prediction data that confirm H, the predictive hypothesis. Since the models inside the ensemble are dependent, we'll assign varying probabilities for each one. Why? Because the more dependent a model is, we'll assign less probability than the other, which is less dependent. In other words, we'll not assign an equal value to each result, even though ensemble is robust insofar as the consecutive model make the same prediction. That is, probability of small d1 given small m1 is not equal to probability of small d2 given small m2, is not equal to probability of small d3 given small m3 ... is not equal to probability of small d10 given small m10. So we identify probability of small d1 given m1 is equal to d1, probability of d2 given m2 as capital D2, probability of d3, small d3 given m3 is equal to capital D3, and probability of small d10 given small m2 is equal to d10. Since all models under H are dependent, we can estimate now the probability of D given H in terms of Bayes' theorem, using the theorem of probabilistic dependence when all prediction data are dependent. To recapitulate, utilizing the model being dependent and averaging over the probability of capital D1 ... D10 over the hypothesis H and not H, we use equation 1 to find an increased confidence in predictive hypothesis. Again, equation 1 says that data confirms the hypothesis if posterior probability of each is higher than the prior. So now, this is a very few mathematical equation will show. For a better grasp of the equation, again, equation 1 is that data confirms H if the posterior probability is higher than the prior. So that's equation 1. We express it in terms of A, B, and C, and we call it equation 2. So A is the posterior probability H given D is equal to B divided by B plus C. So we have to just remember B divided by B plus C. So now A is this whole, posterior probability of H, predictive hypothesis, given D1, comma, D2, ... Dn. B is probability of H multiplied by so this is the prior probability multiplied by probability D1, comma, D2, ... Dn given H, the predictive hypothesis. And C is the negation of the predictive hypothesis, the prior, multiplied by probability of D1, ... Dn given not H. So this is, so the equation we need to remember is A equal to B divided by B plus C. And this is A, B, and C. And what we are going to do is that we are going to expand the B term using the probabilistic dependency notion. And we are going to expand the C by using probabilistic dependencies. So now, for again, same thing we repeated, equation is A equal to B divided by B plus C, and here is B. And if you expand that problem by using the prior probability H multiplied the probabilistic dependencies, then we get the whole thing, and we don't need to care about unless you really want to see that. So again, equation A, B divided by B plus C. So here is C. So C is the prior probability of not H multiplied by using the dependency theorems, and this is how the expansion looks like. Now, since each model is dependent on the rest, which following theorem of probabilistic dependencies means that successive model is less reliable in providing unequivocal information about our confidence in H. So we assign decreasing probability values for each term in B and C. Remember, the equation 2 is A equal to B divided by B plus C. So we need to know B terms, values of each term under B. We need to know each term under C. So we could also assign increasing probability values because we are multiplying all terms in B and C separately. Consider the values for B, table 1 and table 2 I'm going to show soon. Beginning with a value for each term in B, ending with a value for each term with C, while probability of H is 0.5, going with Parker's recommendation. So here is we are just showing the equation in case we can get a good grip of what we're doing. So we are just taking the first few terms in B. Again, A equal to B divided by B plus C, and B, the first few terms of B are B term is prior probability of H. Then the first term under likelihood is the probability of D1 given H. And the second term is the probability of D2 given H1, comma D1, and blah, 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 blah. So we assign probability H is 0.5, probability of D1 given H, 0.32, probability of D2 given H and D1 equal to 0.29. Now, why are this value endorsed? Why you can work with that? So 0.5 following Parker, D1 given H is 0.32 compared to probability of D2 given H1 and D1 is 0.29. D1, probability of D1, the likelihood or the probability of D1 given H is less dependent than probability of D2 given H1, comma D1, and so on. That's why we assign lesser value than this one. So this is how we calculate the whole thing. So this is the B terms, and what we told we just did, as more dependent the models are, we are giving less and less value. So you got a number for B, and you'll see. So this is how we did. So now here we are looking at the terms in C. So again, we are looking at the first few terms in C. Again, the equation is A equal to B divided by B plus C. So here is the C term, some of the first three terms of C. So probability H, 0.5, probability of D1 given not H, 0.3, probability of D2 given not H, comma D1, 0.27. Why these values? Probability of not H, the prior probability is 0.5, following Parker, that's what she recommended. Probability of D1 given not H, 0.3, compared to probability of D2 given not H, and D2 is 0.27. D1 given a probability of D1 given not H is less dependent probability than probability of D2 given not H, comma D1. So if you compare probability of D1 given H, that means the first term except the prior in B, we assign 0.32 compared to D1 given not H, which is 0.3. So data is more likely under H because that's the predictive hypothesis, under the denial of the hypothesis. Hence, 0.2 is less than under point H, since 0.2 is 0.2 less under the denial of the predictive hypothesis than for under H. So here's a C term, we followed what I said and we got the number. And so what we got, beginning with probability of prior probability of not H, 0.5, each term in C is receiving lesser value than its counterpart in B because we assume that each model's data would be slightly less likely under not H, under H. So again, the equation is A equal to B divided by B plus C. So we got A, the posterior probability of H is close to 0.84. Okay, so it's a very high confirmation value. So despite, although we thought if the models inside the ensemble model are dependent, then we may not get the increased confidence, but we have showed that we have an increased confidence in the ensemble model prediction. And which is, and the confirmation account says that data confirms the hypothesis if the posterior probability is higher than prior. So the posterior probability is 0.84 and the prior is 0.5. So it's significantly higher, so it has increased confidence in the ensemble model prediction. So note that the individual likelihood used for each term in B is only 2% greater than its counterpart in C. So now, how is this possible? We thought it won't be the case. So again, the equation is A equal to B divided by B plus C. So we divide this equation, the numerator and denominator by B when B is defined, B is not equal to 0. We get A equal to 1 divided by 1 plus C divided by B. So we get a posterior probability if the C column values are smaller than the B column values pairwise. If this is not the case, then we can permute values into the columns to satisfy the condition. If the C column values are much smaller than B, then A equal to 1 is attained very quickly. Note that the pairwise property, the property I said that columns C value will be a little less than the B value, is not a necessary but a sufficient condition for increased confidence. So now we showed that if the models inside the ensemble are dependent, we can get an increased confidence in ensemble model prediction. Now we are exploring the possibility that maybe the data-driven model, the D1, capital D1, capital D2, D3 are taken. Let's see for the argument's sake, taken to be conditionally independent given H and not H. We'll still use equation 1. Equation 1 says that data confirms H if the posterior probability is higher than the prior, to calculate the value using Bayes' theorem. However, in this case, B and C column, the likelihoods of the individuals model are independent of all the preceding and the following terms. Okay, so if we assume each term for B is 0.6, why doing that? Because each model is independent, and therefore each model will provide equal amount of support for confirming then the probability of data given the model is more likely. So while assuming probability H equal to 0.5, we obtain B equal to 0.003. And if we assign each term the value 0.3 under not H, as likelihood need not satisfy the probability theory, then you got C equal to 0.435 zeros followed by 295. Then actually A is confirmed, is handsomely almost approximating 1. So tables 3 and 4 show the value of each term in B and C. So since a D1, capital D1 ... D10 is independent of one another, each provides strong confirmation for H. We get probability of D1 given H is equal to probability D2 given H equal to ... probability of D10 given H equal to 0.6. Likewise, probability of D1 given not H equal to probability D2 given not H ... probability of D10 given not H is equal to 0.3. So here is this terms, values assigned to the terms B. Again, equation is A equal to B divided by B plus C. So here's the term under B. And here's the values under the C terms, and we got the value. And so Bayesian difference continued. It does not make any difference whether each term under B gets assigned 0.3 and each term under C got 0.1. We are able to receive very high confidence in H anyway, so long as the C column values are smaller than the B value, pairwise. So if they're much smaller, then A is attained, A equal to 1 is attained quickly. So what we have learned is that it is irrelevant whether the models inside the ensemble model are dependent or independent. We can still get an increased confidence in the predictive hypothesis H, so long we satisfy the formal condition. So we are almost at the end. So coda. So we argued against conventional wisdom in philosophy of climate science. We contended that we should increase our we should increase our confidence in the predictive hypothesis H, irrespective of the fact whether the models are dependent or independent. We provided a formal condition under which we are able to reach that confidence. So therefore, we conclude that things are not as epistemologically bleak as Parker and Knutti and their co-authors take them to be. Thank you.
Thanks a lot, Prasanta. You can unshare your screen now.
Sorry, what do you say?
Could you please unshare your screen? So that we can see you on the screen.
Stop sharing.
Stop sharing, yes, yeah, excellent, thanks a lot, yeah. So thanks very much for that rich and interesting paper. I'm sure people have questions about it. So I'll open up the floor to questions shortly. Just as a reminder for those who've already attended and for those, I guess, a new piece of information for those who are attending for the first time. If you would like to ask a question, please use the raise hand function in Zoom. The way you would use that is you would go to the participant list, which you can access at the bottom of your screen, of your Zoom screen. So go to the participant list. At the bottom of the participant list, there should be a button allowing you to raise your hand. Please raise your hand if you have a question. I will come to you in the order in which I see hands being raised. Also, I request that you restrict yourself to one question at a time. If you have multiple questions, please ask one question, then raise your hand again, and I'll come back to you as I cycle through the remaining questions. Okay, Prajit has a question. Go ahead, Prajit. Please unmute the mic and ask a question.
Hi, Prasanta.
Hey, Prajit.
Thanks a lot for this lovely paper. I was just wondering whether these 10 different small models on the basis of which you calculate first the probability of the small d1s and so on. And then you go on to calculate the probability of capital D, D1 and D2 and so on. Whether such calculations of, let's say D2, when you calculate probability of capital D2, you conditionalize with respect to capital D1 as well as H for B, right? And so similarly, when you go to D3, you conditionalize over D1, D2, and H. Am I right?
Yes, yes, something like that.
So now the question is whether the ordering matters. You start with D2 and then go to D1, D3. And the answer is that probably it shouldn't matter.
Yes.
Right? Now
yes, that's exactly right.
Right.
Because the multiplication A into B, so you can multiply B into A.
Exactly. So now in that case, isn't that therefore an intuition which says that they are in some sense independent?
Okay, good question.
Okay.
Should I continue? Or do you want to say something more?
Please. No, I just wanted to know that, because if you take that these to be independent, then the further question, of course, I will have is they can be correlated because of sharing, but still they remain independent of each other. Would that be a right way of visualizing?
So what we did, we are just following the definition of probabilistic dependencies. So whatever the probabilistic dependencies will tell us, we'll do that. So we are just following the probabilistic dependencies, exactly the theorem of probabilistic dependencies. Now I can tell you, probably you know it already, So here is the interesting thing. Knutti writes, and with his co-author, that they are, and I have a part. So they are allowing. So they, at some place they are saying, well, we are not talking about probabilistic dependence or independence, but they are still using statistical dependence in other places. So if what you're saying that, so actually, Prasanta, what you are taking the data, the model data as actually independent. So that's what the climate scientists like Parker, philosophers of climate scientists like Parker are saying. So they might agree with you about that point, but we have two responses. One is that we are just following the mathematical statistical definition of dependencies, and whatever the prior deductive method will tell us, we'll do that. One. Second is that it is unclear that they are using statistical probabilistic dependencies and all those things in other places, but they are skeptical, but they did not spell out the way you are talking about.
Thanks, Prasanta.
Am I clear what I'm saying?
Yeah,
Prajit?
yeah, absolutely. Thanks.
Thank you, Prajit. Abhishek, please go ahead with your question.
Yeah. Thank you so for the talk. I have a couple of questions, but I guess I'll restrict myself to just one. Just like kind of recapitulate what you argued for. You said that it is possible that data confirms a particular hypothesis in question, even if the models under that hypothesis, they are probabilistically dependent. When a particular condition that is specified, that gets fulfilled, and the condition is that the joint probability of the hypothesis and data is greater than the joint probability of negation of the hypothesis and the data. Now, it seems to me that Parker, I have not read that paper, it seems to me that Parker, etc., they seem to be arguing that it is this thing which is not really, valid in case of ensemble modeling. So, I mean, if I use your terminology B and C, then it seems to me what they are saying is that B, or a probability of data given the probability of data and hypothesis, because they have assumed P of X is equal to P of naught S, so the denominator term does not really matter. So they seem to be arguing that probability of data, the joint probability of data and hypothesis is not significantly greater than the joint probability of data and the negation of the hypothesis. You seem to have proven, on the other hand, that you can get confirmation if this condition is not met. You have assumed that this condition is not met. So I'm really unsure how the formal condition that you, said you are saying that you have identified, which can guide us in deciding whether or not the ensemble the model is confirmed. I don't get how that condition really would be of any use in this debate, because it seems that your condition that B is greater than C is precisely what they are saying, that it is not the case, that B is not equal greater than C. So I'm unsure how the condition would really work out in the debate.
So let me see, Abhishek, whether I understood your question. You will tell me whether I got it. Okay. So you're saying that we have that pairwise condition between the column terms under column B and under terms under column C. Yep. The pairwise condition is that the probability of the terms in the sum of the probability of under B. Okay. So that would be greater than the sum of the terms under C. And you said that this is our sufficient condition for increased confidence, but you are saying that is exactly what they're questioning. Is it your question, this one?
Yeah.
So that's a very good question. Actually, Kevin responded to that thing in our paper. And so let me try to see whether I remembered it. It is in our paper, we responded. So exactly the same point Kevin raised, that they will, and so I think the way we did it in our paper, and I probably sent the paper, but I can send you one more time. I think the response is that climate model prediction, the model, they can make some prediction of some future time. And suppose if they don't, if our prediction, so if what you're doing does not match with exact predictions, a climate model does not make exact prediction. So if it does not make prediction, that's fine. But if it does, then we can still say that probability of data given that, yes, still we can say that probability of data given the predictive hypothesis is greater than probability of D given not H. So maybe I need to be a little more clearer, but actually we tackled that question. That's a very good question. We did tackle it. So, but our answer basically is that that climate model prediction that long do not make that prediction. And if that case, if it doesn't match, that's okay. But if it match, then no such precise prediction climate model prediction makes. And I should have a better response. I will send you the paper. We have a response to that. Thank you.
I'll come back for the second question.
Yeah, Abhishek, if you have another question, just raise your hand again on the screen. I'll come back to you. Mark Taper has a question.
There we go. I should be unmuted.
Yes, you are.
Can you hear me?
Yeah, please go ahead. Yeah.
Still want to go back to my first question.
Okay.
You're using the term confidence.
Yes.
And I am unclear as to how you're distinguishing confidence from belief.
So, the confidence is belief, and for the Bayesian, they talk about credible interval. You know more than I know, probably. So we are. So it is confidence is. That's how the Bayesian use the term, at least in philosophy of science. So increase confidence means increase confirmation.
Okay, terribly annoying because frequentists coin confidence to separate themselves from.
Right.
To give
but
a similar.
But Bayesian do have the term credible interval, right? That is yes. Also some sort of.
So you mean by confidence a tightening yes. of the credible interval?
That's right. That's right.
Okay.
Okay. Thank you. So by the way, I think I saw someone raise a hand, but I'm not sure exactly. Please either raise your hand on the Zoom app itself, or if, just type it in the chat and let me know if you want to ask a question, and I will come to you. But since Abhishek is the only one with the hand up right now, let me ask my own question before coming back to him. So thanks a lot, first of all, Prasanta, for the talk. I'm a little confused by one of the assumptions you make. So you talk about how if the models are independent, then the likelihoods associated with all the different prediction data will be the same. And if the models are dependent, then the likelihoods will be decreasing. So you have like probability of D2 given H and D1 is less than the probability of D1 given H. And this is, I guess you're arguing that this is a kind of implication of the dependence of the models, this kind of, I don't see why that would be true at all. I think you can have dependent models in the sense that, I mean, maybe we just mean dependence and independence in different senses. But what I would take dependence of models to be here is that conditional on the hypothesis, there's no further dependence between the models, right? That's what independence of the models would be. So so independent models would be ones where probability of D1 and D2 given H is equal to probability of D1 given H multiplied by probability of D2 given H. But that condition by itself, I don't think entails the constraint that you're talking about, that if you have dependence, then you will have this kind of decreasing probability as you look at each additional piece of evidence. In fact, intuitively at least, it seems to me that if you have dependent models, let's say you just have multiple copies of the identical model, so they're all as dependent as you could possibly have it, right? If the models are identical, then the probability of D2, whatever the prediction data of the second model is, given D1 and H, would be close to 1, right? Or it would be 1 because you've already conditionalized on D1, which is an identical model. So you've conditionalized on the same model, on the same data, and now you're asking what is the probability of the data given that data. So that would go up to 1 rather than going down below what it would have been earlier. So If you have identical models, it seems like if you conditionalize on the first model, then you just get probability 1 for every subsequent model. Whereas you seem to place a constraint on dependence that the probabilities have to go down as you conditionalize on more and more models. I don't understand where that comes from, I guess.
So, yes, very good question, Tarun. So you are saying the constraint I'm using or the assumptions that I'm using to assign a lesser probabilistic value when the models are dependent compared to when the models are independent. So that rationale you are questioning, right?
Right. Yeah.
So here we are just trying to follow what the, those who are much more well-known in the climate science, what they're saying. So basically what their point is that when models are dependent, that means models are dependent means they, inside that ensemble model, there are so many models, and those models share algorithm, the same sort of things they're using it, legacy code, they have, share codes and all those kinds of things. So because each model under the big model, they share all sorts of things. So, so the idea is that then we cannot really say that each model under the ensemble model will provide a very strong confirmation for the whole thing when you take them into account. But and there are very few independent models are there. That's they're saying. So independent models means, we have we showed a slide where, and it actually this slide is the ideas derived from Steve Running's suggestion. So they're saying even though models are not independent, but they are not clones of each other. So they are looking at like one thing we're looking at from different sides. So each model inside the model, they're giving a different perspective of the whole thing. And that's why they think that, so that is one of the reasons why different models, so that means they provide a different perspective, and more models there are, and they're saying that, H is true, so that should provide more confirmation. So the point is that we are just following what they're saying. So the following is that we are using more dependent model is a less probability value we're assigning, whereas independent model. So the last part of the question I didn't give you the answer is that you are saying if they have the same hypothesis, but each of them is given different perspective of the same model. So that's how my response. Am I clear?
So I understand the point you're making about how, having dependent models will, if the models are strongly dependent, then that each additional model will add very little confirmation to the hypothesis.
Yes.
What that seems to mean is simply that the probability of H given D1 and D2 will be very close, or maybe identical to the probability of H just given D1. That adding models, conditionalizing on more and more models, conditionalizing H on more and more models will not increase the probability.
No, we are doing probability of small d1 given small m1. So these are all likelihoods, and then we'll gather the data and increase the confirmation. So we are calculating the posted probability of the model, predictive hypothesis, right? But the predictive hypothesis contains lots of models inside it.
No, I understand that.
Okay.
I think so maybe let me go back to my question here. So let's say that you have two identical models, two models that are exactly the same, right? So your small d1 given m1, where m1 is the first model, it gives you capital D1. Small probability of small d2 given m2, where m2 is your second model, gives you capital D2. Now, presumably here, D1 and D2 will be the same, but let's ignore that for a second. Let's separate them out as D1 and D2. And so now you have probability of D1 given H, your hypothesis that you're concerned with. Right?
One more time, what do you say, probability of?
D1 given H, the likelihood associated with the first piece of predictive data.
Right.
And then you have the probability of D2 given H and D1.
Yeah? Yes.
And the argument we were making was that second, if the models are dependent, then that second probability will be smaller than the first probability.
Right.
But think about the case of identical models. If the models are genuinely identical, then D1 and D2 are identical, right? There is no difference there. That conditionalizing on one piece of predictive data already gives you probability one, what you know for sure what the second piece of predictive data is going to say, because it's the result of an identical model, right?
That's right.
And so probability of D2 given H and D1 will be 1. It won't be less than the probability of D1 given H. It will in fact be 1, because your probability of D2 given H and D1, you're already conditionalizing on the first model, which is identical to the model you're looking at.
Oh, no, that cannot be probability 1. Then there is a fundamental error in our paper. That cannot be probability 1. So you are saying, so you are saying probability of D1 given H, whatever probability we assign,
right,
versus the probability of D2 given H1, comma D1,
right,
and D1.
Yeah.
So you are saying, since we are conditionalizing on D1 already, so actually this is, we are saying conditional probability, but this is all likelihood function going on.
Sure, yeah, that's true. But
so the conditional probability is actually, so the probability of D1 given H is actually proportional to probability of D1 and H divided by probability H. Sure. So it's not equal to, so you are saying that if we conditionalize, so the second one is the probability of D2 given H1, right?
Given H and D1, sorry. Probability of D2 given?
Yes, probability of D2, yes, probability of D2 given H1 means probability of D2 given H and D1.
Yes.
And since we are conditionalizing on D1, the probability should be a 1.
If the models are identical. Yeah.
Because the D1 is the same D1, so we are conditionalizing on it. But we are not conditionalizing it. It is not conditionalization at all. It is, we are doing likelihood calculation because it's a proportional one. And
likelihood is still a conditionalization, right? I mean, maybe we'll come back to this. Yeah,
likelihood, but we'll do that. This is an important point, and I disagree with you here.
Okay. We can talk about that. I don't want to take up too much time, so maybe we can discuss this later. Yeah. Jyoti has a question. Go ahead, Jyoti.
Hello. Thanks for the talk, Professor.
Hi, Jyoti.
Hello. In any large system like climate model simulations, or for that matter, banking system or healthcare, there is always going to be sharing of codes, reuse of legacy codes among models. So how do we understand the notion of being dependent and being correlated such that we are able to differentiate between the two?
Jyoti, are you done?
Yeah, yes.
So please tell me whether I understood your question first. So what you're saying that in climate model and health science, right? Did you mention health science? Did you?
Yeah, like for that matter, like any large system, be like it
any
can
large
be banking system
where
or healthcare.
And where you share all the information, where the models are dependent and correlated.
So there is.
I missed the question.
No worries. I'll repeat it again. So in any large system, be it banking system or healthcare, there is always going to be models that work together as a unit. Like there is always going to be some kind of dependency. Like suppose in banking system, there is always going to be like, or each model is going to access a database. So there is always going to be some kind of dependency. But in the paper, the notion of dependency and the way the correlation has been used is slightly like interchangeably. So how do we understand these two notions such that in a system like this, like climate model simulation, such that we are able to understand them in order to like, so that we are able to differentiate between them. The notion of being dependency among models, and the notion of like correlation among models in a system like this.
Should I respond now? Are you done?
Yeah, sure.
So you were saying in the large model system in a healthcare or climate science where there are a lot of models are used. So how to understand or whether to understand those dependencies in terms of dependencies or correlation. But two things. First is that we need to know the context of the sign. So I cannot say anything much more detail what is going on in healthcare system and others. So it's the expert can tell whether the models are used in what sense. But what I pointed out, what we pointed out is that in climate science literature, they are using the word more probabilistic model dependencies and correlation in the same term. They don't need to do that. Actually, there is this conflation. They are actually talking about model dependencies. That is my point.
Thank you.
Welcome.
Okay, thanks, Jyoti. Abhishek, you have another question? Go ahead.
Yeah, so I wanted to ask really about, it probably relates to the specifics of the article that you are answering to. What if we interpret this thing about the dependence that, or the correlation that Parker and Knutti, they seem to be talking about? What if we interpret it a bit more liberally? What if we do not think of it as a probabilistic dependence? So, I mean, it seems to me what a person might be saying in this regard when they say that the biases are correlated. So different models that go into the ensemble, they would be, for instance, doing the same. So, for instance, underestimating the forcing that is due to melting of polar caps. So, one particular source of error could be getting compounded in the different models, which could be leading us to, or which could ask us to not really believe that the joint probability of data and hypothesis is much greater than the joint probability of data and the negation of the hypothesis. So, I mean, if we interpret it in this sense, so probably this is a question about how do you see yourself and this particular paper in the larger scheme of things. If we interpret the notion of the biases being correlated instead of the models being dependent in a more liberal fashion, then could we say that the argument to some extent is correct, that we really do not have much confidence, however we understand it, in saying that the models, they confirm the hypothesis in question.
So let me see, Abhishek, whether I understood your question. So you saying that if you take their views, that means, Wendy Parker and Knutti's view is that biases are correlated, but it's not the model. They are correlated, but models are dependent. What is exactly the question? So
they would not really be probabilistically. I mean, they might be giving it as a reason for why we should expect the joint probability of D given H to be less than the joint probability of D given not H. So the reason would not, I mean, probably the reason is not that they are probabilistically dependent, but the fact that all the models in the ensemble, they have the same bias. For instance, all of them could be underestimating a particular type of climate forcing. So if we interpret their comments in this light, then how does it position your views in the scheme of the larger debate?
Let me see whether I understand. So, Abhishek, are you saying that to take their view in a more charitable way,
yes.
In the following way, if you attribute them saying that because the biases are correlated, that's why models are dependent, and if you take it, then is it? I'm not still fully.
No, I'm saying that what is being said is that because the biases are correlated, we do not have enough or our confidence in saying that P D given H is not greater than P D given not H. So it seems to me that what they are claiming is this condition, that P D given H is not greater than or not significantly greater than P D given not H. And the reason could be not probabilistic dependence between models, but a kind of correlation of biases. So all the models making the same erroneous assumption about how fast the polar caps would melt, etc.
Okay, so I think I got your question. Your question is that to take their view in a more charitable way, to say that actually what they're saying, because the biases across all the small models inside the ensemble models are correlated, therefore probability of data given the predictive hypothesis is not substantially higher than probability of data given the negation of the hypothesis. Are you saying that?
Yes.
So, yeah, but still, okay. So why? But we are saying that even though, so basically you are shifting the argument that don't take the models to be dependent. So you are going from if X1, Y are correlated, then they are dependent. Are you saying something like that? So then that holds, but it still does not. It still
So,
does
for
not,
instance, sorry.
it still does not show. It still does not show that we fail to show that we have an increased confidence in increased more confidence in confirmation of the ensemble model. But previously, the objection you raised, that is probably more serious. And I have a response, and that is in our paper. And probably I didn't do a good job in responding that part. But that's only you can say that your current point is that because biases are correlated, therefore they think the probability of D given H cannot be substantially higher than probability of D given not H. But we showed that whether the models are dependent or independent, we can still have confirmation. And but the previous question probably is much more strong. Okay, that's it. I can say that. Obviously.
Okay. Thanks, Abhishek. Mark, you have another question? Please go ahead.
Yeah. Well, more comments. I think a lot of this discussion is getting caught up in and failure to distinguish between the redundancy of models and the dependency of the models as random objects. So models could be dependent as random variables, and they could be redundant in terms of what they're saying. And I'm not clear that those two kinds of dependencies, if you want, are being sorted out properly. So you were going at that too by discussing whether or not the models were all identical. That would be a redundancy, but they could have, once you start getting into a Bayesian framework and putting priors on them and making them random objects, they could be dependent in that framework. And I think that's causing a fair amount of difficulty. Fundamentally, and I think that what we're talking about is whether or not models have independent information about, have both joint and independent information about the data that they're predicting. Okay, so if they share some information, that should be taken into share some predictive ability, that needs to be taken into consideration. What will help the situation in a joint model is if various different models make different errors, and then those errors can be may be averaged out by an ensemble or a joint prediction. You can ascertain that by looking at the ability of the ensemble model to predict data that has already occurred relative to the various individual models. So it goes back to basic confirmation of your predictions in data that you already have, and then you have to make your glib projections out. So the ensemble may or may not do better, but you can test it by looking at data that has already occurred. Okay, that's enough for right now.
So basically what Mark, you are saying that things are much more complex than the way our example tried to show. And you are saying that something being models being dependent. So in two senses of model being dependent. One is model being as a random variable. Are you talking about that one or the other one? Yes.
I'm talking about both of them. So you can have, if you start treating it as a random variable, then there's dependencies there. And that's up in the prior structure. But there are also redundancies. In other words, if you have a linear regression and you have variables x1, x2, x3 in one regression, and you have another model which has in their predictive variables x2 and x3, there's a redundancy between those two models. There's shared information between those two models. And this is something that, people in regression contexts have dealt with. And, looking to the question of whether or not you should add another model, another predictive variable, which essentially is creating another model. A variable that might have been highly informative if it was the first variable that was put into your regression equation, you predict, may turn out not to be informative at all if you've already added 2 or 3 other variables. So that's a redundancy in the models, in the ability of a model to make a prediction. And that's different from.
Right.
Okay,
but Mark, basically what we have done is just followed the way Parker and the people, other people, especially Parker's work, is how she, being a pretty well-known philosopher of science and climate science, so how she formulated the whole problem, and we followed that formulation and showed how we can have a increased confidence. So basically, that's the model and the hypothesis. It's true that we are using the model and hypothesis in the same sense, but basically,
I'm not contesting your conclusions there.
No, I'm saying that we are basically following the outlines she has worked on, and we are following that and try to show how we can have increased confidence. And so you are saying in a good way, you are saying that maybe we just need to increase and be careful about all the lots of complexities. But here we have just example how we can work on that thing. So that is the response.
Yeah.
Okay. Thanks, Mark. Are there any other questions? I don't see any immediate questions at the moment. So maybe I will try to follow up a little bit on what I was talking about earlier. Maybe so I think maybe it'll help if I just clarify. Maybe I'm misunderstanding exactly what you mean by the data and the hypothesis here. So I take it that so the small m's I get are the individual models in your ensemble. What are the small d's? The small d's, not the capital D's. The small d
are the data under M1. So probability of small d1 given M1.
Right, but what is the small d1 there? Like what kind of data is it? Is it just is it observed data? Is it is it a prediction of your model? Is it an observation you make? What is it?
Yeah, some could be observation. Yes, how basically what it says, how likely is that particular data given the model, and that's a data. So that data could be that data could be generated by computer simulation, or so yeah, that could be generated by or some past data. That is also possible too.
Okay, so the reason I'm confused is because you have a different d, small d, for every small m. So you have D1 given M1, D2 given M2. If it was just observational data, then presumably you're testing all the models against the same observational data, right? You don't have different observations for every individual model.
Yeah, it is possible too. Yeah, each data could be, so probably D1 may be different data from the D2. Yeah, and it's very likely they're different data.
So I'm not sure what exactly you mean here. So when we look at, say, the CMIP5 ensemble, you have a number of different models. The kind of past, so you're saying the past, so there's a couple of different things that are going on here. So those models make different predictions. This is true. So if you're trying to predict some climate variable, say you're trying to predict climate sensitivity, those models give you different values for climate sensitivity and different ranges and so on. But what you seem to be suggesting here is the past data that is used to train those models is different. And this might also be true, right? So are you talking about the past data used to train those models? Because that then, no, it can't be that. So I'm trying to figure out what exactly the small d's would be in this particular case.
So remember what he said, that each small M1, small M1, M2, M3, each of them is a model inside the big ensemble model, right? Yeah, that I know. So each model looks at a different aspect of the big picture. So one of them is looking at the wet, how wet the western part of the United States will be. So those data coming. Some people are saying what's the temperature will be around that time. So the different sort of data coming from the different models.
But I mean, when the IPCC and so on make estimates for climate variables using an ensemble method, it's because all of the different models are predicting the same variable, right? They're all giving us predictions for climate sensitivity. They're just giving us different predictions. And therefore, because we have a number of different models that are giving us, say, different predictions for the same variable, they use an ensemble and use some kind of ensemble average as the actual estimate for that variable, rather than any individual model's prediction. So, I mean, if you had individual models giving predictions for different variables, one of them predicting precipitation, the other one predicting temperature, then there would be no reasonable aggregation method where one could come up with an ensemble prediction, because these are just different variables, right? The reason one engages in ensemble techniques in the first place is because the models are predicting the same variable. And so presumably, then they are making predictions about the same data.
Yes, but the thing is that suppose they are predicting what would be the temperature of western part of United States in 2080, for example. Now, maybe those temperature are connected to how wet the land will be, what would be the, how much is the water content in other part of the world. So these are all, each of them is a different set of data, all accumulated to contribute the temperature predictive hypothesis that the western part of the United States in 2018, blah, blah, blah. So these are all connected, contributing to the predictive hypothesis. I'm assuming this is something like that.
Okay, assuming that is true. So here is intuitively why I would think that, look, that independence would be valuable, independence of models would be valuable in terms of confirmation. And the reason is essentially this. So this is how it would appear. So let's say we have some hypothesis about the climate system, right? Let's say the hypothesis is that the equilibrium climate sensitivity of the globe as a whole is this much, right? Some value. That is a hypothesis. And all the models point in that direction, let's say, for whatever reason, right? Now, the worry is that all the models point in that same direction, not because all the models are kind of independent models that are all kind of giving us independent evidence for this hypothesis, but that all the models point in the same direction because all of the models share certain fundamental algorithms, assumptions, something like this, and those shared biases are what lead to to them pointing in the same direction. And if that was the case, the agreement would not really be evidence for that. That's a worry, at least. The agreement would not really be evidence for that particular hypothesis. Now, the way I would try to think about that probabilistically is that your model, that under the independence case, what you would want is that, look, the only reason the models are making the same prediction is because of because they share some kind of the actual causal process that they're using to predict the future of the system. That is the only thing they share. What they share is the actual, is the actual representative part, what actually gets the causes right in the real world, right? That's all we want them to share. We don't want them to share other things that might not be connected to the real world in the same way. And what, so I would think that would mean then, I mean, I'm trying to think, I'm trying to connect this to this, I think, I don't know if you read this paper that I wrote a while ago on robustness and independent evidence, where we made the argument that, look, if you have two pieces of evidence that are independent, conditional on a hypothesis, then you can prove that if both pieces of evidence are independently confirmatory, then the conjunction will also be confirmatory, right? So we argued that conditional probabilistic independence is sufficient for the conjunction to be confirmatory if each conjunct is confirmatory. But if you don't have conditional probabilistic independence, you can often construct cases where each individual piece of evidence confirms, but the conjunction actually disconfirms, right? So this is a paper from a few years ago. I think there was a talk you attended, but it was a long time ago, so maybe
right
for you to remember this. And if that is the notion of independence being relied on here, then what independence, all that independence means is that the probability of D2 given H and D1 should be equal to the probability of D2 given H. It doesn't mean the probability of D2 given H should be equal to the probability of D1 given H, which is the condition you assume, right? So just to type out the two conditions in the chat just to make it clear. So this seems to be the condition you assume will hold in under the case of independence, right? Hold on, I've just typed it in the chat. That is what you assume to be the case if you have genuine independence of models.
Right, that's right.
Whereas right. I would say that, look, the actual condition for independence of models is this, what I'm typing now. That condition, which is that adding D1 to your likelihood doesn't change the degree to which H confirms D2. Right, that's what it means for D1 and D2 to be genuinely independent. That so adding D1 adds no further information.
Show me one more time. So you're doing conditional independence here.
Yeah, this is in the chat. The second thing that I've posted is what I think is. See it in the chat.
Yeah, no.
So if you go to the bottom of the screen and you click on the chat button, you should see a chat on the side.
Okay, so. So probability of D2 and H1.
So the top one is the one that you have in your paper as a condition for independence.
So the two response. Actually, this is the paper I was looking for, and yours and I. So that's why I asked whether you wrote a paper. So that's remember I have. Right, you presented the paper at Kanpur IIT, and then it came out in Philosophy of Science. I was looking for this paper and asked Dawn about it. So I need that paper first. Second thing is that so we first wrote the paper and was supposed to be presented at 20 San Francisco APA, where you use the conditional independence. And Eric Winsberg, who was supposed to be the official commentator, he said that you cannot use conditional independence because of the very strong constraint. So then we moved to model independence. So conditional independence is a very strong assumption. And so that's one of the things. But I will look at your paper one more time, and I'll get to you. First, let me look at the paper. But conditional independence is what they are questioning all along, that you cannot use. And I thought I used conditional independence so to avoid independence. but he said basically you are, so basically that is some sort of independence they're using. So that's one of the reasons we moved to the model. I look at it. I'll be honest with you. I'll read your paper. I'll get back.
So the paper, I've sent a link where you can access the paper if you.
Yes. Okay. Is there any way you can send me in my email so that
I can also mail it to you? Yeah, that's right. Yeah.
Please do that. That's the paper I was looking for.
Yeah. Okay.
That is the paper. Anyway. Okay. Anything else?
Any other questions? Okay. It seems like there are no further questions from people in the group. So I think
it's a very good discussion. It's a very, very good discussion. Is it in general like that? Is it general like that?
What? I'm sorry. What do you mean?
So I like the question very much. You know, these are genuinely good question, excellent question.
Yeah,
but I'm saying, where the discussion previously was like that.
Yeah, I think our discussions so far have actually been quite good, and yeah, our participants have been very active. They've been very good questions. So I
always like that.
Sessions. Yeah.
But why so many few people showed up in my talk?
So I think that there were more people while you're giving the talk. I think often in the question and answer period, people start dropping out. I guess.
No, I saw how many people were there. But anyway, that doesn't matter. Thank you for inviting me. But don't kindly send me the link.
I'll email you the paper. Yeah. And we should talk about this more. I think there's a lot more.
Priyadarshi, you let me go so easily. Anything else? So it looks like I can leave now.
Okay, so yeah, I think we'll call it to a close then. There seem to be no further.
And are you happy with the whole thing?
Yes, I mean, I shouldn't speak for everyone, but I at least am very happy. I'm sure others are also very happy. So thank you very much for very clear presentation and for engaging with us so productively and
kindly send me the paper. Please.
And I will definitely send you the paper. And thanks for being here at an early hour for you. Okay. Yes, okay. So with that, I'll call this session to a close. Thank you all for attending. Thanks, Prasanta, again for your talk. And I hope to see you all next week when we will have...
yes, very happy, Prasanta, very happy.
Thank you, Priyadarshi. Thank you. Good to see you.
So next week we will have Mazvita Chirimuta, and I hope to see all of you back for that talk. So we'll see you all next week.